Okay, so in this video you will learn about the driving forces of the world's oceans and how their oceanographic features operate and interact with each other. First, we begin with a wave. An ocean wave is the undulation of the water surface caused by a disturbance, usually wind, and they transport energy through oscillations. The anatomy of a wave is vital to understanding how different wave types are formed and how they interact with each other. Here are a few basic definitions. The trough is the lowest point of the wave. The crest is the highest point of the wave. The wavelength is the length between the highest point of each crest from point A to point B. The wave height is the distance between the highest point on the crest and the lowest point of the trough. The wave period, which is the time for point A to reach point B. The wave frequency, the number of wave crests that pass at point A per second. When wind blows over the ocean, energy is transferred to the surface layers of water through friction. The agitation generates movement that creates gravity waves. Air pressure is what causes the waves to propagate. When winds faster than 2.5 meters per second blow continuously for an extended amount of time, a wave can start to have an effect on the environment around it. The wind catches the troughs and pushes the crest like sails, sustaining the wave and increasing the wave height. Water particles do not move in a wave pattern. Instead, they make circular motions known as orbitals. At the crest, the particle moves up and forward with the wave. At the trough, the particles move down and backwards away from the wave direction. The water particles move forward more than they move back, meaning that a small net of mass will slowly creep forward in the direction of the wave. This is known as wave drift. Orbitals decrease steadily with depth, decreasing in energy until the depth is equal to 1/2 of the wavelength. At this point, there is so little energy that the molecules can no longer move in their orbits. Capillary waves are waves where the surface tension is the returning force, characterized by a wave period less than 0.1 seconds. Gravity waves are waves where gravity is the restoring force, and they are characterized by a wave period longer than 0.1 seconds. A chop is 1 to 10 seconds, a swell is 10 to 30 seconds, a seiche is 30 to 5 minutes, and a tsunami is 5 minutes to 10 minutes. Tides can be from 12 hours to 24 hours as they are diurnal. The size and energy of a wave is influenced by how long the wind has been blowing, the strength of the wind, and the fetch, which is the distance the wind blows over the surface of water. Wave height is often determined by using significant wave height, which equals an average of the top 1/3 of wave heights. To calculate wind speed, we use the wave speed equation. Celerity, which is another word for speed, equals the frequency times the wavelength. Deep water waves are waves traveling in water deeper than half the wavelength of the wave. Shallow water waves are waves traveling in water shallower than 1/20th of the wavelength of the wave. Deep water waves are near spherical, while shallow water waves become more elliptical as the topography of the beach compresses the molecules. This causes the bottom layers to slow down while the surface layers of water continue to travel around at the original velocity, causing the wave to break. Tides are considered to be shallow water waves due to their long wavelengths. All layers of water are affected by the tides. When a wave approaches a landmass, it turns to a shallow water wave and slows down as the orbitals become more elliptical. This causes the wave to change shape and run parallel to the coast, eventually breaking when the surface layers of water travel faster than the deeper layers. These are known as breakers. Typically, there are 4 types of breakers. They are spilling, plunging, surging, and collapsing. Spilling breakers often occur on shallow gradient beaches where the crest deepens until it becomes unstable, resulting in a cascade of white water down the face of the wave. Plunging breakers occur on steeper gradients or in locations where there is an abrupt change in topography, such as a sandbar or reef. The crest is hurtled forward, plunging into the trough, releasing the majority of its energy on impact. Surging breakers occur on the steepest of gradient shores. They appear flat and low and surge up the beach, reflecting the majority of their energy back out to sea. Collapsing waves are a combination between plunging and surging breakers. However, the crest does not fully break, but still gets deeper, consequently creating foam. The breakers are described using a parameter known as the Irabarren number. E0 is the height of the wave in deep water in meters, and EB is the height of the wave at breaking point. Calculating with these will give you different values. However, putting them into the table will still give you the same result. Waves can be constructive or destructive. Constructive waves have lower energy and deposit material forming beaches. They are characterized by having a strong swash and weak backwash with a low wave height and long wavelength. Constructive waves are low frequency and subsequently hit the shore 6 to 9 times a minute. Destructive waves are created by powerful winds that have been blowing for a long time over a long fetch. They have high energy and remove beach deposits eroding the beach. They have weaker swash compared to its backwash. Destructive waves have high frequency with short wavelength and high wave height. They also have a higher frequency, typically hitting the shore 10 to 15 times a minute. Coriolis is an inertial force caused by the rotation of the Earth, where objects in motion appear to be deflected off their intended path. In the northern hemisphere, objects are deflected to the right, and in the southern hemisphere, objects are deflected to the left. When wind blows across the ocean surface, Coriolis deflects the water a few degrees to the right in the northern hemisphere and to the left in the southern hemisphere. Friction causes the layers beneath to move, which is again deflected, resulting in an Ekman spiral. The mass transport occurs at 90 degrees to the left in the northern hemisphere of the wind direction and to the right in the southern hemisphere. As well as waves, friction also creates currents that generate the circulation of water around the globe. They can be divided into two main categories: surface currents and deep water currents. Surface currents mobilize the first 10% of the water. They're driven predominantly by winds, however tides do have some influence due to the fall and rise of the water. Surface currents distribute heat from the equator to the poles. An example of a surface current is the Gulf Stream. Deep water currents mobilize the deeper, denser 90% of the water. They are driven by friction from the surface layers of water dragging on the layers underneath, and cold, salty water from the poles towards the tropics. Temperatures and salinity cause density changes in the water. If the changes are significant, density currents can occur. The saltier water is, the more dense it is, and the warmer the water is, the less dense it is. This forms the thermocline circulation. A great example of this is the Great Oceanic Conveyor Belt. The Great Oceanic Conveyor Belt drives water transportation worldwide. It is vital to move warm, salty water to the poles and for the poles to deliver cool water to the tropics. This ensures a pleasant climate for us to live in. Currents can lead to gyres, which are loops of circulations of water found in the major ocean basins. There are 5 major gyres: ones that flow clockwise in the northern hemisphere, the North Atlantic and Pacific, and ones that flow counterclockwise in the southern hemisphere, which are the South Atlantic, South Pacific, and Indian Ocean. This is because of the Earth's rotation and the Coriolis effect. The closest gyre to the UK is the North Atlantic gyre. Land masses interact and lead to the refraction and diffraction of surface currents, resulting in the gyres. In the northern hemisphere, a clockwise circulation is described as anticyclonic, and in the southern hemisphere, circulations are anticlockwise and referred to as cyclonic. Cyclonic winds generate surface divergence, creating upwelling areas because Ekman's drift pushes water away from the center, creating a low pressure gradient. Water rises from the depths to fill the gap. The opposite happens in the southern hemisphere. Upwelling and downwelling occurs as a result of Ekman transport. Due to the mass transport caused by Ekmans, water is pushed away from the shore. Water upwells from the depths to balance the pressure difference. The opposite happens with downwelling. Mass water being transported means that the water is put under pressure and sinks to the depth as new water is piled on top of it. These processes play a large role in deep water currents and biologically very important. To explain tidal propagation, we use two theories. Equilibrium tidal theory is an idealized model, meaning you must first imagine the Earth to be completely spherical and completely submerged in water to an equal depth. Its useful foundation in describing tidal patterns on Earth, the position and attraction of the Sun and the Moon from the Earth, gravitational and centripetal forces from the Sun-Earth and Moon-Earth orbits form tidal bulges. The bulges are always pulled towards the Sun and Moon. The Earth simply rotates underneath them. Extreme tides are created when the Sun and Moon are in alignment with each other, and the least extreme is when the Sun and Moon are at right angles from each other. These are known as neap and spring tides. Dynamic theory is a more realistic model as it takes into consideration the effects land masses and shallow water with the creation of tides. Due to the maximum speed of a shallow water wave, there is a lag of water behind the Sun and the Moon. However, this is not the case with higher latitude as the wave does not have much distance to travel. Tidal basins such as the North Sea slosh water around the amphidronic system, pictured above, in an anti-clockwise rotation and clockwise in the southern hemisphere. A full rotation takes 12 hours, which is why we have diurnal tides. Climate change will have a detrimental impact to the way the Earth's oceans operate currently. Global warming heats up the planet and consequently makes the water less dense at the poles, which means it will be more difficult to sink, causing the conveyor belt to buckle. Furthermore, climate change could make processes more energetic. This means bigger storms and more winds, and bigger waves, which could influence the currents.